So there are a couple of things that I want to discuss before we move forward. Something very quick. Let's say you have two contiguous elements. One is the nice thing about PFEM is that you can actually tailor the polynomial order that you want in each particular element. So this is a very nice feature of the method because you can say you have one element equals that has a very high polynomial interpolation, p equals 10, and then the neighboring elements are p equals 2. And you can actually do that because of all these nice properties that we saw, right? The fact that all your edge functions are going to vanish. But then if you have a situation like that when you're actually mixing polynomial interpolations, right? Then what do you do at the edge, at the common edge? What do you choose? If I have p equals 10 on one and p equals 2 on the neighboring element, so which one you choose? Well, that's really up to you. You can say, well, I want to keep p equals 10 along the edge or p equals 2. That's up to you, okay? And so there are these two options that you can choose. So I could write that down. Let's do it very quick. Let's do it very quick. So we're running out of time, and I really want to cover the part on boundary conditions today. So let's say you have let's say this is your mesh, and here you have p equals 1, p equals 2. So then you have two rules that you can follow, of course. Either you choose one or the other one. So the mean rule or the max rule. And this is what happens at edges with different. So how are we going to write this? Let's see. Okay, the last thing, and then we move to boundary conditions, is the mapping of the geometry. And as we said, in the case of the PFEM in one dimension, is the same here. Yeah. Okay, so right now we are discussing this possibility that you have elements that have different polynomial interpolations, because you can do this in PFEM. In HFEM is much harder to do this, particularly with Lagrangian elements, because you have to enforce, you have these hanging nodes that you somehow you have to enforce continuity. But with PFEM this is very straightforward, because you can say, well, how about I have this element p equals 10 and the neighboring p equals 2? Well, you can do that here. And then the question is, what happens at the common edge? Well, you can choose whether you want along that edge to have p equals 10 or p equals 2. That is up to you, but you can do both. Okay, that is just a little thing to talk about for completeness. And the other thing was the mapping of the geometry. And similarly to what we studied in the 1D case, we can ramp up our polynomial interpolation all the way we want, but then the geometry didn't make sense to go higher than linear for our 1D case. Well, in 2D, what is your guess? What is normally done? Of course, we have the linear case, right? And then we're talking about the same thing. And for the particular case of the quad, we have 4 shake functions, so we have them like this. This is the way now we are. These are vectors, right? So xi is the coordinate of node I, and phi I, as you know, is the linear, or in this case bilinear, shape function. So that is one choice. Who has another choice? Yeah, we can go quadratic, why not? And this is nice because, you know, with a quadratic, with a parabola, we can already approximate very complex curves, right? I mean, of course, as long as you go down also in mesh size, which is a HP extension. But, you know, with a quadratic mapping, you can already improve on the geometry. So now we are talking about 8 functions. And then let's say we're talking about an element where the geometry is defined like this. And there is yet another one that has been proposed that is called blending functions. And this is to represent some sort of curve that you have an exact representation. Let's say you have a curve and your curve is whatever you want. So you can actually introduce that into the mapping, but I will not discuss this very much because it's actually a bit complex. But I am putting this here for completeness and for letting you know that you can actually incorporate into your formulation exact geometries as well. Okay, so let's say you have a circle, you can map that circle that you have an exact representation, a mathematical equation into this formulation, and be able to use that type of mapping, right? To include that mapping to get the Jacobian. Of course, there are other issues, right? Because then integration becomes an issue. And sometimes when you are, in a way, when you are thinking about exact geometry, right? You are thinking about more into the terms of superparametric formulations. Okay, we're no longer in subparametric as before when we're having our linear interpolation for the geometry and our, let's say, quartic interpolation for the field. Now it's the other way around. We're exactly representing the geometry, so we are in the realm of superparametric formulations. And these have a very big issue. When you're dealing with superparametric formulations, sometimes you can lose your rigid body modes. So, but you know, I don't want to get into all of this detail. Just wanted to put this out there just for completeness, okay? And this is to represent particular geometries. Exactly. For example, circles, etc. Okay. And that's it. That's pretty much the method. And there is a very important issue, as usual. Perhaps the biggest issue in all of this is implementing what? What do you think is the main issue for PFEM in 2D? So far, it looks okay, right? I mean, it looks a bit challenging, but I'm sure that I give you a very simple problem in 2D, and I ask you to solve it with quadratic functions, and then you're fine. Except for what? The boundary conditions is the issue. Yeah, and this is a big issue in PFEM. And perhaps it's the most complex part of implementing PFEM in 2D. And the reason for that is that now, you say you have a quadratic, or let's say you have a cubic polynomial function over the edge where you want to impose the boundary condition. The problem now is that you don't have this Kronecker delta property between functions anymore. And so you have to do something tricky to enforce non-essential boundary conditions there. Yeah, sorry, non-homogeneous essential boundary conditions. So we're going to talk a little bit about this, and of course this is better explained in that book chapter, but I just wanted to finish this lecture to talk about this issue because I think it's important when you're discussing PFEM. So none so the issue is that's our potato. Now we have an element here. Of course, that element comes from some master element. Right? And then we want to enforce some function ux of s. We want to enforce that displacement. So our function is the g. Okay, g's are going to be our function, gx, and these are function of some sort of curve s that starts here. This is s equals 0, and this is s equals 1. Okay. And the same for the y component, because we have a two-dimensional problem. So let's say we're dealing with displacement, so we have two components. All right, so we're going to look first at what happens with our standard Lagrangian elements, or the ones that we're always using in PFAM. Okay. And I want to look at that particular edge, so I'm looking again at this element, right? So I want to, of course, be able to see what's going on along that edge where I'm trying to enforce the boundary condition. And so I have, let's take, this is going to be node 2, 6, 10, 14, and 3. So there are, in that edge, 5 nodes. So let's say eta of the first node is equal to -1. Eta 1 is equal to -0.5. Eta 2 is equal to 0. Eta 3 is equal to 0.5. And eta 4 is equal to 1. So you see already that I'm using a high order Lagrange element. And what I want to do is to enforce a function that looks, it's a function that looks something like this, let's say. So it's a nonlinear function, and this is s equals 0 and s equals 1, right? So I am basically 2, 3, 4, 5 nodes. So because of the nice property of the, this Kronecker delta property of the Lagrange functions, it's super straightforward to do this with Lagrange elements. So if you actually write the field, let's just take the x component of that, and we're interested in looking at that x component at 1 eta, right? So 1 eta means that I'm looking at this line, psi equals 1, and then eta. So you can actually write this as, well, before we have used the symbol phi, phi and n are actually used interchangeably in the finite element literature. So let's stick to phi so that you guys, so phi 2, and then times u2 plus phi 3, 1 eta u3 plus phi 6, yeah, 1 eta u6 plus n 10, 1 eta u10 plus n14. and I change again to n, this should be phi u14. So that would be the expression of the displacement field along that edge. Yeah. And now the only thing you do is you basically evaluate that expression at every one of those nodes, and because of the nice Kronecker delta property, you immediately get the coefficient that you need to impose there. Okay? So we get ux at 1, eta 0, so we evaluate at the first point right here, right, with this coordinate. And for that, you get phi2 at 1, eta 0, u2, all the other terms vanish, and because phi2 at that particular location is equal to 1, we get u2, and we set that degree of freedom to gx evaluated at that eta 0. Super straightforward. And you do the same with the rest. Eta 1, so now we're talking about my phi6, 1, eta 1, u6, which is equal to u6, which is equal to gx evaluated at eta 1, and so on. And you do the same. Very straightforward, because of the Kronecker delta property. So that is a nice thing about these Lagrange shape functions. So let's see what happens when PFEM is used. So who can tell me what's going to happen? Because now I need to evaluate that expression. It's the same as before in a way. These are the linear vertex functions plus phi6 and these are the edge functions. But these functions, if you remember, they don't have that nice Kronecker delta property anymore, right? So if you remember, actually, that function phi6 is what we call our quadratic Legendre polynomial that we use to construct the shape function. So we call that phi hat 2 of eta. This is basically p equals 2. And then this one here would be the cubic one. So this is our cubic term. And finally, this last one is going to be our quartic. Yeah? So what do we do now? Any ideas? We have the same interpolating function as we had before, but now the problem is that all those higher order shape functions do not have this Kronecker delta property, so we cannot evaluate them immediately. So what can we do? Who has any ideas?
System, linear system, and then subscribe the condition that they should all be zero at those particular points, and then solve for that.
So yeah, you're going in the right track. You read the book?
No.
So then I'm impressed. So you are going in the right track. So we actually come up with some sort of system that we need to solve. So we have to enforce this somehow. There are many ways to do this. You can come up with some sort of error function and then try to minimize that error. But a nice way to do this is just to evaluate that function at some points, come up with some system, and then get those coefficients. Right? You're solving a linear system of equations. So that is the first way. So any ideas? What are the nice points for this? What are the points where I'm going to evaluate? You could basically do this with any points along that line, right? Because I mean, to solve for, let's say, 5 degrees of freedom, how many equations I need? 5, and no one tell us not to put. I mean, the order could be anything, but of course you would want to space those in a nice way so that they actually are representative of the function that you are trying to impose. Yeah, doesn't make sense to have all these 5 evaluations, very close to one another. And so, who has an idea what is a natural choice for this?
At the edges?
No, everything is evaluated at the edges. At the edge. Yeah. So one nice choice for this is to interpolate this function at Gauss-Lobato points. Anyone knows anything about Gauss-Lobato integration? Who knows Gauss-Lobato? Yeah, you know, but who else? So this is a different type of quadrature, right? So in the past lectures we have seen Gaussian quadrature, or what is called a Gauss-Legendre type of quadrature, where all your integration points are taken internally, right? The Gauss-Lobato actually also uses the endpoints. And that is the reason why this is a nice choice for this problem, because we have those points as part of our problem. So the endpoints are considered as well as integration points. Okay. So what we do is, of course, we take those Gauss-Lobato points that, again, as in the Gauss-Legendre, these are all tabulated. So you say between -1 and 1, I want to have an integration rule, Gaussian-Lobato integration rule of, let's say, I don't know, this number of points. So all this information is tabulated, right? So you get this, the location of the Gauss points, and you get the weights associated to those Gauss points. So it's pretty much the same thing as what we have seen before for the Gauss-Legendre integration rule, but now we are considering the endpoints as well. Okay. So we do that. We evaluate at some points. Zero, 1, and we get 5 equations, and then we solve for the 5 by 5 system. But there is a nice thing here, because if you remember our high order shake functions, they are all vanishing at the locations of the linear function. So at the end points, right, they are all vanishing. So in fact, if you just take the linear functions, since this is the same as a standard FEM, the linear functions have this Kronecker delta property, which is nice. And so in fact, do we actually need to solve a 5 by 5 system? Or not? No. So what is the system we're going to solve? 3 by 3. Yeah. So once you have those degrees of freedom that you obtain locally because you are solving a local problem, then you proceed as a standard FEM, and you can enforce those degrees of freedom in the same way you have been doing it all along for standard FEM. Okay? So then proceed as usual. And this is one way to solve this problem. Yeah? There is a second way to do this, but I will not discuss it in detail. I'm just going to state it because, you know, for more information, you have the book chapter. You can read about it there. But you can come up with some sort of error and do some sort of least square type of minimization of the error along that edge. And this is, again, you're solving a system of equations to obtain those generalized degrees of freedom. Yeah, so we have what is called an L2 projection. Yeah, and then you can learn a little bit more about this in the book chapter. Are there any questions about PFEM in 2D? Because this is basically all I want to say for PFEM in 2 dimensions. As you saw, the hardest part is to implement boundary conditions that are non-zero boundary conditions. That is the hardest part. Of course, you have to think about integration, right? Because when you are ramping up the polynomial interpolation order, you also have to take care of Gaussian integration. So you have to increase the number of Gauss points. But that's it. I mean, it's very straightforward. No questions about PFEM? Yeah, so the number of integration points, of course, is defined again for 2 dimensions. You have to find a number of Gauss points that integrates a function exactly. And so if we look, for example, at the quadrangular element, you can take the linear rules, right, for 1D, and then it's basically that rule Cartesian in the other direction. So let's say if you are thinking about a linear function, how many Gauss points you need in 1D to integrate a linear function? Two. So 1 Gauss point integrate exactly a polynomial of degree. 1. No. 2. Yes. 2.
No, 1 Gauss point.
Minus 1. 1. So a linear function is integrated in 1D by 1 Gauss point only. Now, if we go now to quadratic, we need how many Gauss points? 2. Because 2 times 2, 4 minus 1, 3. So 2 Gauss points can integrate all the way up to 3. Right? So now if we take a look at the 2D problem, then of course you look at what you need to integrate, and then you say, well, now I do Cartesian, this number of points in this direction, and this number of points. So then you're talking about a 2 by 2 rule for that type of polynomial. Yeah? Now, for triangles, it's a different story, because for triangles, there is really a different set of rules that you can actually use. So for p equals 1, you use the center of the triangle. For p equals 2, then you have to use 3 Gauss points, and all of this information is tabulated out there. So you just look for integration rules for triangles, and then you get basically the rule, the number of points that you have to use, and the weights associated, and the location, of course, of those points. So this is very straightforward. Okay, that's it. That's all I wanted to do with PFEM. Before we finish this course, I want to share something else, but I'm going to share this in a different video because I